We watch modern language models write functioning code, compose rhyming poetry, and answer incredibly complex questions. When you see these responses spark to life on your screen, it feels like you are interacting with a conscious mind. But beneath the surface, there is no conscious thought. A large language model, or LLM, is simply running a highly advanced statistical forecast. It calculates the most likely continuation of any given text. It is essentially playing a massive, rapid-fire game of guess the next word, a task even human brains struggle to do flawlessly when sentences get complicated. Early attempts at this, using older AI architectures, like recurrent neural networks, routinely failed. Because they processed information exactly like we do, sequentially, reading left to right, they would literally run out of memory and forget the beginning of a long paragraph by the time they reached the end. To solve this memory bottleneck, engineers had to stop teaching machines to read like humans. They needed a completely new structural framework. This diagram shows the transformer architecture, the engineering breakthrough that allowed models to bypass the constraints of human memory. Notice how the data flows at the bottom. Instead of scanning a sentence word by word, a transformer ingests the entire input sequence simultaneously, in parallel. By absorbing all the data at the exact same moment, the AI can instantly scan the entire dataset. This parallel processing provides the raw capacity needed to make accurate predictions. But feeding an entire paragraph into a machine all at once creates an immediate problem. Without sequential reading, the grammatical order collapses, and the sentence turns into a jumbled mess of disconnected words. Looking closer at the schematic, you'll see positional encoding. This mathematical technique tags every word with its absolute and relative location. This provides a fixed spatial layout, ensuring the order is preserved before deeper analysis. With these position tags in place, the AI possesses a perfectly organized map of the entire text. Now it can begin analyzing the actual meaning. This analysis happens through the attention mechanism. Think of it as a tireless data analyst, investigating how strongly every single word relates to all the others. As this graphic demonstrates, the model uses a bidirectional context. It looks outward in both directions from a target word, analyzing the surrounding data from the left and the right simultaneously. It uses this surrounding data to calculate specific attention scores. These scores mathematically weigh how relevant every word in the sentence is to the word currently being processed. This animation shows how the word bank interacts with its neighbors to resolve ambiguity. If the sentence mentions water, the attention scores will heavily link bank to river rather than to financial terms. These attention weights actually alter the core data of the word itself. Depending on the surrounding context, the model creates distinct mathematical representations for the exact same word. Through this mechanism, the machine translates the messy, subjective nuances of human language into precise, solvable equations. Once the context is perfectly weighted and the relationships are mapped, the model has to actually make its prediction. This section of the model's output shows a leaderboard of probabilities. It calculates a strict array of likelihoods for the missing or upcoming word. There is no intuition involved here. The system simply locks in the mathematical fictor with the highest percentage score. The intelligence we think we are interacting with is ultimately nothing more than the execution of this highly calculated statistical selection. When you zoom out from the microscopic view of a single guess, the true scale and speed of this process becomes apparent. The model is recursive. As soon as it predicts a single word, it immediately feeds that generated guess back into itself as new input context. By repeating this loop in a matter of milliseconds, the model rapidly chains together full paragraphs, detailed essays, and complex blocks of code. What appears to be a continuous, flowing stream of thought is actually thousands of rapid-fire, isolated calculations happening in sequence. But because the entire system is strictly probabilistic, it carries an inherent vulnerability. Its guesses are entirely bound by the text it was trained on. This leads to LLM bias. If certain perspectives, prejudices, or stereotypes are overrepresented in the human-generated training data, the model will naturally replicate them. When a model produces a biased output, it isn't making a malicious decision. It is directly reflecting the flawed human statistics that drive its attention scores. LLMs map human context mathematically. they have not reached human consciousness. Recognizing LLMs as statistical mirrors strips away the sci-fi fear. They aren't thinking entities. They are simply reflections of our own language, staring back at us.